Okay, friends, let's see what is the next question. My fourth question is, why doesn't gradient descent method always converge, doesn't converge to the same point? So this is around the gradient descent. Again, this is a very fundamental question, gradient descent. So what is gradient descent? Gradient descent is nothing but an optimization algorithm. And what kind of optimization? It's not a closed solution. You are not solving an equation. It's an iterative mechanism or iterative algorithm where you are taking a small steps towards the downhill, right? In essence, that's what it is, right? What is gradient descent? You calculate the gradient, you go in the negative direction of the gradient a small step, and you multiply it by learning rate, and then you take a small steps to reach to the minima. That's what it is, right? That's what gradient descent is. Now let's see why. The question is not about what gradient descent is, but its question is that why sometimes it doesn't converge, or it doesn't converge to the same point, at least if you repeat the experiment, right? So friends, you have to understand that gradient descent will always find the global minima in case of a function which is convex in nature. So what you are doing, let's say you start, it's a ball shape, this is the ball shape function, so this is called convex functions, right? So our linear regression, okay, or logistic regression, these are the examples of convex functions, right? So their cost function is essentially convex, right? And what you are doing, you are calculating the gradient at this point, right? And you are going the negative direction of the gradient. And how you are going, you are taking a baby step, a small step, and multiplied by something which is called learning rate, right? This is essentially the basics of gradient descent. Now the question is that why it always doesn't converge. So one reason could be that, hey, my function is not truly convex function. What do you mean by not truly convex function? Let's say in two-dimensional space itself, if you have a function like this, let's assume you have a function like this, okay? If you start from this point, if your data is initialized at this point, this is my global minima, right? Global minima. If you start at this point or any of this in this particular valley, right, you will reach to the global minima. But what if you are starting over here? What will happen? This is my local minima. Local minima. You'll keep taking the small step over here, and the gradient descent will finally converge, and it will think this as the minima, because after that, if you do, your stopping criteria will be met, that the tolerance, what we call, right, the net reduction in my learning, or net reduction in my cost function is very low. Once it becomes flatter, what it will mean? It will mean my del by del x, or whatever that thing is, del c by del x, right? This becomes very small, right? It is becoming flatter and flatter, right? Multiplied by alpha negative, right? This quantity will become very small. So I'm not further reducing my cost function. This is my cost function, or j theta, okay? I'm not further reducing. So if you start from here, you will be stuck here, and you will get the local minima. By chance, if you are coming over here, you will get global minima. So the moral of the story is that in case of a true convex function, a true ball-shaped function like this, right? A true ball-shaped function like this, you are guaranteed by your gradient descent algorithm that you will reach to the global minima. But if the function is not truly convex, right? This is something which is not truly convex. In that particular case, you are not guaranteed. You can be stuck at the local minima. So one case, if you initialize it here, you will reach here. Another case, you initialize it here, you will reach here, right? This point. Another case, you initialize here, you reach here, the global minima, right? So if the function is not truly convex, you can reach at the different levels, okay? So that's what. Now, what is the example of a truly convex function? Your logistic regression, your linear regression, these are truly convex. Their cost function is truly convex, right? Anything which is quadratic in nature will be truly convex. In deep learning, no, that's not truly convex, right? So in case of deep learning, there is a high chance that you will be stuck at the local minima. But the local minima is good enough, okay? That's why we are okay with this thing. And there are certain techniques of how you initialize to increase your chances to reach to the global minima. Those things are the part of the deep learning framework. Okay. The other thing is stochasticity. What is stochasticity? Looks a big fancy term, but essentially it means probabilistic. Okay. By chance, by probability. That's what we do in SGD or stochastic gradient descent. We take one sample at each point, right? So if we take one sample at each point, it will keep hovering around the minimum, because we are not doing the batch gradient descent. We are doing a stochastic gradient descent. So there is an inherent difference, that there will be a variability associated with my one observation can start pointing me in a completely different direction. Another observation will start pointing me. So a SGD algorithm will never converge finally. It will keep hovering around the minima, but it will never converge, right? So that could be the another reason. The learning rate could be another reason, right? Let's say in this particular case, if we assume a very high learning rate, what will happen? We'll just go in the other side of the minima, and it will start diverging in this particular case, right? It can happen. So if you have a very poor choice of learning rate, the whether it's SGD or batch gradient descent or mini batch gradient descent, it will not converge, it will diverge, right? So these could be the different scenario that, or different reasons why gradient descent doesn't always converge. And again, over here also, for friends, I have a YouTube video, okay, where I have tried to explain the gradient descent. Let me just show you over here in the playlist. Okay, where is the gradient descent? Okay, yeah, this is the playlist for gradient descent. If you need more information about it, you can always go ahead and read it. Okay.